Hello and welcome to a lesson on differentiation of polynomial functions. We'll begin from the general formula for differentiating a power of x. We'll look at a range of examples and then put these powers of x together to form polynomial functions. We'll then investigate graphically what the gradient function of a polynomial function actually is. Having done that, we'll take a typical easy exam question where we use differentiation to find the gradient of a polynomial curve at a given point and the equation of a tangent and normal to that curve at that given point. The basic rule for differentiating a power of x. One form of notation is d by dx. That means differentiate with respect to x. And if we differentiate x to the power n, the n comes to the front and the power drops by 1. So we get n x to the power n minus 1. And if we have a look over here, I've got a similar example with a constant a already at the front. If we differentiate ax to the power n, again the n comes to the front and is multiplied by the a that's already there. And again the power of x drops by 1 to n minus 1. Let's have a look at some examples. Differentiate x to the power 6. And we get 6 comes to the front, 6 x to the power, lower the power by 1 and it's down to 5. So the differential of x to the 6 is 6x to the 5. Differentiate x cubed and we get 3x squared. 3 coming to the front, the power, and the power dropping by 1. Differentiate x squared, we get 2x to the power 1. But we won't write the x to the power 1, we'll just write 2x. What if we differentiate x? Well, we can think of x as x to the 1. So we get 1x to the power 0. But x to the power 0 is 1, so we've got 1 times 1. So the differential is just 1. However, an easier way of thinking of that is if we were considering the line y equals x, the gradient of that line is 1. And that's what differentiation is for a polynomial. It's the gradient of the curve, or in this case, the gradient of a straight line. What if we differentiate a constant c? Well, we could think of that as cx to the power 0, because x to the power 0 is 1. And we'd multiply by the 0 at the front, and we'd get 0 times cx to the minus 1. But the 0 would drive the answer to 0 when we multiply by 0. So, if we differentiate a constant, it's 0. Now I've gone through those last two to point out that the rule is consistent when we're differentiating x or a constant, but it's not the way we typically think of it. What's the gradient of the line y equals 6? It's a horizontal line, so the gradient is 0. What's the gradient of the line y equals 5? It's a horizontal line, so the gradient is 0. So it's easier just to memorize the fact that when you differentiate a constant, you get 0. Let's now look at some examples with constants already built in. So differentiate 5x to the power 6. The 6 comes to the front and is multiplied by the 5 that's already there. So we get 30x to the power, lower the power of x by 1, it's 30x to the 5. Differentiate 4x cubed. 3 times 4 is 12, so we get 12x to the power, lower it by 1 to 2, so it's 12x squared. Differentiate 7x squared. 2 times 7 is 14, and this becomes x to the 1, we just write it as x. Differentiate 3x. Well, 3x to the 1 times the 3 is 3, and x to the 0 is just 1. But again, it's easier to think, well, if that was y equals 3x, the gradient of y equals 3x is 3. So the differential of a number of x's is just a number. If we were differentiating minus 9x, it would be minus 9. And finally, differentiating a constant, as we've already said, think of y equals 8, a horizontal line, the gradient is always 0. When you differentiate a constant, it disappears. We'll now link together powers of x to form polynomials, and we'll differentiate those. We'll also introduce two new types of notation. We've seen d by dx, now we can look at dy by dx. If we're differentiating y, we call it dy by dx. And that gives us the gradient function for y. So when I differentiate y here, dy by dx equals, differentiate x to the 4, we get 4x cubed. Differentiate plus 3x squared, and we get plus 6x. Next example, dy by dx, the derivative of y with respect to x, is equal to, if I differentiate 3x cubed, we get 9x squared. Differentiate minus 7x, we get minus 7. Differentiate the constant plus 2, and we get 0. It doesn't contribute. So the differential here, dy by dx, is 9x squared minus 7. Now then, a different form of notation. If instead of y equals something, we've got fx, where f is a function of x, the derivative with respect to x is written as f dash of x. So f dash of x is equal to, differentiate x squared, we get 2x. Differentiate minus 3x, we get minus 3. Differentiate minus 5, and it disappears. So f dash of x, the derivative of fx, is 2x minus 3. And one final example, f dash of x is equal to, differentiate x cubed, we get 3x squared. Differentiate minus 2x squared, we get minus 4x. The 2 multiplied by the minus 2 give me minus 4. And if we differentiate plus 3x, we get plus 3. So there are 4 examples of differentiating polynomials. We'll now go on to investigate the gradient function of polynomials graphically. I've chosen 2 functions to investigate, a cubic function and a quartic function. So let's begin by differentiating them. Y equals x cubed minus 2x means that dy by dx is equal to, differentiate x cubed, we get 3x squared. Differentiate minus 2x, we get minus 2. Let's differentiate this one as well. Dy by dx is equal to, differentiate x to the 4, we get 4x cubed. Differentiate minus 2x cubed, we get minus 6x squared. Differentiate minus x squared, we get minus 2x. And finally differentiate plus 2x, we get plus 2. So what do we see? We see that when we differentiate a cubic, we end up with a quadratic. So the gradient function of a cubic is a quadratic function. If we differentiate a quartic, we end up with a cubic. So the gradient function of a quartic is a cubic function. Let's see if we can use autograph to show us what's going on. First of all, the cubic. Y equals x cubed minus 2x. And what I'm going to do here is I'm going to ask autograph to draw the gradient function. Just give me a minute to set it up. Okay, ready to draw the graph. And what it's going to do is it's going to put the gradient function on, and it's going to plot the value of the gradient as the x-coordinate moves along. Now it's not quite on screen, it's too steep at the moment, but here it comes. You'll find the gradient is about plus 3 at the moment. Now it's about plus 2, it's getting less and less, and it'll be 0 when the gradient is horizontal. Now it's getting negative, getting more negative as it goes around the curve, getting more negative, but eventually it starts to get less negative as it heads towards this next turning point. There it is, the slope now is getting less negative, And by the time it gets to this turning point, we'll find the gradient will be plotted at 0. But then it just keeps on getting steeper and steeper as it goes round the curve. And by the time it's finished, I've stopped plotted it when it gets to 2, we'll see that the gradient function is indeed a quadratic. It's the 3x squared minus 2 curve. Right, let's now have a look at the other example, which was a quartic. X to the power 4 minus 2x cubed minus x squared plus 2x. I'm going to do exactly the same thing, ask it to give me the gradient curve. Right, ready to plot again. This time the gradient's steeply negative, so it can't plot it at the moment, it's off screen. But we'll find it comes on down here somewhere at minus 4. There it goes, minus 4, and it's getting less negative, heading up towards 0 at the turning point. Now the gradient's positive, getting more positive, but then it starts getting less positive as it heads towards that next turning point. When it becomes horizontal, the gradient will be plotted as 0. And off it goes to the next turning point, negative gradient, getting more negative, until eventually it stops getting more negative and becomes less negative. When we get to this turning point here with the gradient, its value will be 0 because it's horizontal, and then it gets steeper and steeper. And so we see the gradient function that's being plotted is indeed a cubic function, that well-recognized shape of the blue dotted line. Well, hopefully that's given you some idea of how the gradient function arises in polynomials. We'll now go on to look at examples of exam type questions. Our first main example, example 1. Consider the curve y equals x cubed minus 2x squared minus x minus 12. Part 1, find the gradient when x equals 2, and parts 2 and 3, find the equation of the tangent to the curve when x equals 2, and find the equation of the normal to the curve when x equals 2. We begin then by finding dy by dx. Y equals x cubed minus 2x squared minus x minus 12 means that dy by dx is equal to 3x squared minus 4x minus 1. When I differentiate the minus 12, it disappears. Now I want to find the gradient when x is 2. Well, the gradient of the curve is given by dy by dx. So we say when x equals 2, dy by dx is equal to 3 multiplied by 2 squared minus 4 multiplied by 2 minus 1. Well, 2 squared is 4, 3 fours are 12. Minus 4 times 2 is minus 8, minus 1. And 12 minus 8 minus 1 is 3. So dy by dx is 3. But that is the gradient of the curve. So gradient when x equals 2 is 3. So that's the first part done. Now we want to find the equations of the tangent and normal to the curve at the point when x is 2. And to do that, I'm going to need the y coordinate on the curve. So let's first find the y coordinate. And we do that by saying when x equals 2, y equals, and we substitute the value 2 in the equation for y. So it's 2 cubed minus 2 times 2 squared minus 2 minus 12. So y equals 2 cubed is 8, minus 2 times 2 squared, that's minus 8, minus 2 minus 12. So the 8's cancel and I'm left with y equals minus 14. So let's say the point on the curve that we're interested in is the point x is 2, y is minus 14. Now that I've got the point on the curve and I've got the gradient is 3, I can find the equations of the tangent and the normal. So I've written down to remind us here, we're looking at 2 minus 14 with gradient 3. And we're just going to use the formula y minus y1 is equal to mx minus x1. Because the gradient of the curve is defined to be the gradient of the tangent. So I know that the gradient of the curve is 3, so the gradient of the tangent will be 3. And x1, y1 is a point that the tangent passes through, and that's the point 2 minus 14. So I'm going to write y minus the y coordinate minus 14, y minus minus 14 is equal to the gradient 3 times x minus the x coordinate, which is 2. Simplify this, y minus minus 14 is y plus 14 equals 3 times x is 3x, 3 times minus 2 is minus 6. Take the 14 to the other side and we get y equals 3x minus 6 minus 14. Change of sign there. So y is equal to 3x minus 20. And that gives us the equation of the tangent in the form y equals mx plus c. Now the normal. First I need to know the gradient of the normal. Well, the gradient will be minus 1 over 3 because the normal is perpendicular to the tangent and perpendicular gradients have to multiply to minus 1. 3 times minus a third is minus 1. So in other words, we take the 3, think of it as 3 over 1, turn it upside down, change the sign. Now then, same thing again, y minus y1 is equal to mx minus x1. Still the same point, 2 minus 14, so it's y minus minus 14 is equal to minus 1/3 x minus 2. So that becomes y plus 14 on the left hand side is equal to minus 1/3 x, and minus a third times minus 2 is plus 2/3. So I'm now going to take the 14 to the other side. Y equals minus 1/3 x plus 2/3. When I take the 14 across, it becomes minus 14, but we might as well write it in thirds. 14 is 42/3, 3 lots of 14, so it's minus 42/3. And that will give me a final answer for the normal of y equals minus 1/3 x and plus 2/3 minus 42/3 is minus 40/3. And that completes example 1. And that concludes this first lesson on differentiation of polynomial functions. You'll find an exercise that gives you practice differentiating polynomial terms and also provides you with 2 exam type questions similar to the one we've just done. When you've done that, you'll be ready to tackle a lesson on differentiation of polynomial functions investigating stationary points on polynomial curves.